Thank you all. That was really mind expanding for me as well, getting a broader view of this security guarantees you're trying to get on a big system. And I'm going to talk about what's been going on with CVA6 and CHERI, and hopefully catch you all up on what's been going on. It's been a community effort, just like RISC-V in general. And so what about CHERI? CHERI is a project that's been going on for about 15 years, and there's been lots of development, finding out that you can use it as a compiler target. All your pointers can be capabilities. We had MIPS originally. Then there's been a big ARM and RISC-V effort in parallel for a period of time. And now we're at the stage where people want to build chips and they want to sell them. And so we're ratifying a RISC-V standard. There's a couple of commercial designs coming out and a few chips we know about. And we would like to make a reference design, open source design, as you often like to have, so that people who do commercial designs do at least as well as that. And if they don't, at least they can pick that one up and use that one. So what about CVA6? So CVA6 is a active open source project, lots of contributions going in, lots of improvements going in. So we wanted to jump on the CVA6 bandwagon and add CHERI to CVA6 so we could have something that would move along with the times, improve as new extensions come in, and we could see how it composes with all the existing extensions. So the effort to add CHERI to CVA6 actually started at 0 Day Labs in Portugal. Sandro Pinto was around here a few days ago. I don't know if he's here now, but he has a student, Bruno Saw, who did the first extension of adding the university research version of CHERI to CVA6. And at Capabilities Limited, we joined in about a year ago, not quite a year ago now, and talked to Bruno, and he got things together and managed to release the work that he'd done so far, and we helped him finish verification. And then we ported to the new the new candidate for standardization, the RV64Y extension. So that's what I'll talk about today. These are the different areas I'll talk about, how we implemented it, the verification effort that we did, because we'd like it to be something that people can pick up and use, area optimization, and also timing optimization. So implementation. So what is CHERI? So CHERI doubles the size of your register file. So we need to be able to fit 129 bits, which is the 64 bits of the XLEN word, another 64 bits that contain bounds and permissions metadata, and one more bit that tells you whether every 128-bit register and memory word is a valid capability or not. And this is what keeps you from, doesn't allow people to fabricate any pointer that they want in the system, which is an important property for CHERI. So we need memory to appear like 129-bit words. We need the registers to hold 129-bit words, and to check every memory access against a capability. Okay, so we implemented these in CVA6, and there was an initial implementation from Bruno, and then we've tweaked all of them so we can inspect the capability fields of each register. For example, you can get what the permissions are, what the base is, what the length is. Then we have more complicated instructions for manipulating capabilities, like setting the bounds of a capability. And because the bounds format is a kind of floating point, sophisticated format, there's a little logic that goes into that. Then we can do pointer arithmetic while ensuring that the bounds stay the same. Of course, dereferencing capabilities need the bounds to be checked, and we need wider data paths so that we can load and store capabilities themselves, 128-bit words from memory. Then, of course, there's capability control flow as well. So everywhere you have a pointer in the system now has to be a capability. So you jump to pointers as well. So the program counter is now the program counter capability. So we need to be able to track the bounds correctly as we run around. We'll talk about that more today. So initial pipeline changes. Many of this architecture was originated by Bruno. So he added a capability logic unit, the clue, and you need to ask yourself, does your processor have a clue? Maybe not. We had to widen the registers and the forwarding paths and the PC and add CHERI CSR, so that touched quite a lot of the pipeline. And when we extended for the Y extension. As you can imagine, we did a lot of work in the decoder, moving to the new proposed locations for all of these instructions in the decoder. And with the capability logic unit, other than removing a few functions which we don't actually use in the proposed standard, there wasn't, we just called the original functions that Bruno named, and a lot of the work was in the library that implemented the functions to implement the new encoding format for those. And we'll talk about that a little bit as well. So one of the most interesting changes in the proposed standard is a mode switch instruction. So back when we did the MIPS version of CHERI, we saw that there were two distinct operations. One is dereferencing a capability, where you take the bounds of the capability and check them against the address that you're dereferencing and making sure it's in bounds. And the old kind of memory access, where you dereference an integer and you check it against what we call the default data capability. So it's not possible to get around the capability addressing mechanism, but you might be dereferencing integers checked against the default data capability, or you might be dereferencing these new capabilities checking against their bounds. Well, that's a lot of encoding space. So when we moved to RISC-V, we used a capability mode, and we said, well, when you're in capability mode, we'll just assume all the existing loads and stores check their bounds against the bounds in the register of the address. We'll expect the address to be a full capability. But the problem is sometimes you have what we call hybrid code, especially maybe an operating system kernel where it's trapped user space and it's got a bunch of capabilities in the registers, and it now needs to manipulate capabilities a bit, but maybe all of its pointers are just 64-bit integers. So it needs to do both kinds of addressing and mix and match them. So what we did in the original research RISC-V is we introduced a new set of loads and stores with smaller immediate fields that you could use just for doing the alternate mode. Well, that's ugly. Even ARM, when they did their prototype, they did a similar thing. So what we decided to do instead was a very efficient mode switch. So we have one instruction that says, please switch to the other mode, please switch back again. And this was a challenge to implement efficiently. Let's see, do I talk? Oh yeah, this is the slide where I talk about that. So the way we decided to do it, and we specified it because we thought we could implement this way, is to make, even though that mode bit belongs in the program counter capability, we let that bit be owned by the decode stage of the pipeline. So as instructions flow through, we know what the mode bit is in the decode stage. And the moment we see one of these instructions that says, please switch into capability mode, for example, in midstream, we can immediately start decoding into the new mode, so we never have to slow down. And then when we see the next instruction come by, these are completely specified what mode you're switching into in the instruction itself carefully. It doesn't depend on a register value, so that we can precisely track the mode midstream in the decoder. Now, it sounds simple when I say it right now. It sounded simple to us when we started, but it turns out as you flush and have exceptions, you have to track everywhere what your mode bit is. So from that moment on, we did have to send the mode bit attached to each instruction so that we knew how to reconstruct your PC accurately when asked. We'll talk about that a little bit more too. So verification. So we have a capability library we call CHERI caplib that has hardware description language implementations of important capability functions. And we've been working in BlueSpec System Verilog with our research implementations. But Bruno produced actually quite tidy System Verilog versions of these functions. So one of our first jobs at Capabilities Limited in helping him out was to want to verify the equivalence between these two. And we did this with a formal, open source formal tool called Symbiosis, which I gather is not as powerful as Jasper Gold, but it was plenty powerful enough to do equivalence between combinational functions. So we got a nice little verification set up where you can see here many different functions between the two copies of the two libraries that we could assert equivalence between them using a little macro that would generate a wrapper with an assertion at the end saying, no matter what my 64 bits or 128 bits of input are, the output will always be identical between these two. And So we found about 5 bugs in the initial library. One of them was very critical. But more importantly, it greatly accelerated our movement onto the Y extension encoding, where we tried some slightly more aggressive tricks, and we were able to get counterexamples very efficiently in VCD format, so you could just use your waveform viewer to look at what was wrong, and so we were able to quickly converge on completely correct implementations. Okay, so test rig, this was another part of our verification. So far, the way we've verified any CHERI RISC-V processor is using a system called test rig, where we generate random instruction sequences and inject them in. And Bruno implemented test rig graciously in CVA6 so that he could compare against all of our other CHERI RISC-V implementations. But he did it in a simple way where he only had one instruction at a time going through the pipeline. And that was able to get him through most of the architectural implementation of RISC-V. Well, we wanted to do a little better, so Peter Rugg, who works with us, fully pipelined the test rig implementation so that we were filling the pipeline with instructions to uncover all sorts of pipeline bugs, which I'm really glad we did because of some of the optimizations we did later, which we needed that level of verification for. So this is exactly what I was talking about. So for area optimization, when I started to dig in here to look at the mode switch bits, I saw there were copies of the PCC bounds all over, and from our experience we thought this is not necessary, I'd like to improve on this. So what we did is we moved all of the bounds of fundamental fact is you do not need to know the bounds of your PC before the execute stage of the pipeline. And why do you need to know it in execute? It's because in execute you might have a jump and link register, or you might have an AUI PCC that writes your entire PC with the bounds into a register. So at that point you need to know the full PCC. But you don't need to know it before that. And furthermore, almost all your instructions have the same bounds information until you're jumping to another compartment. You generally have the same bounds. So what we did is here's what our new one looks like. We made the issues stage just before execute the owner of the PCC bounds, and we have just one copy of the bounds of PCC right there. And if anybody on the last half of the pipeline asks, what are my bounds? You say, these are your bounds. It's the same as everybody else's bounds. And if an instruction turns up in execute that reads a register value and it's about to jump to it, it reports the new bounds back, and we're able to stall issuing instructions until the last part of the pipeline flushes, which in this case is only 2 instructions in 2 cycles, probably, before we issue the new one. So that means we only really have one copy of the bounds for PCC. And very satisfyingly, the whole front end reverted to what it looked like upstream. So that's a much easier thing to maintain that has no knowledge of capabilities. And we only need to start thinking about the bounds later. As you can imagine, debugging this really benefited from test rig being able to fully pipeline, because every time you threw an exception or needed to redirect, we needed to redirect the bounds into the issue stage and the address all the way back into the beginning of the pipeline. Okay, let's go forward. So we consolidated some execute functions. We didn't need the offset anymore in the proposed standard. And another nice feature was we had these 2 optimized functions that operate on the compressed format directly. One was to change the address and make sure it was still, sorry, I said it the wrong way. One was to perform arithmetic on the address and make sure it was still representable. And the other one was to set the address, and that was a more recent change. And what we decided to try here was just to use the set address as a common shared resource in execute at the end, and simply perform a normal add in the pipeline before. It turns out that passed timing, so we were able to eliminate a bit of area there. And overall, we eliminated about 17% of the execute logic overhead. Not mind-blowing, but an improvement. Hopefully, we'll be able to improve that more. So currently, we have a 42% logic overhead on the Genesis 2 FPGA, and we're hoping to do better. These are our current overheads, which we've only got this together a couple weeks ago, so we're excited to tackle the really big ones and see if we can reduce that further. Timing optimization, really quickly, we did quite a few. But one last one was to make the decode of capabilities when loading from memory in parallel to the byte selection, which we need for loading half words and bytes. And that was the last trick that got us to pass timing at the 50 megahertz that is normally used for CVA6 on the Genesis 2. Software support, we have all sorts of software running on it already. We have OpenSPI, pure capability. We have CHERI BSD, we have CHERI SEL4, all the same things that are running on the Codasip platform, we have now running on our CVA6-CHERI on FPGA. And that's good. I don't know if we have time for questions.
I was a bit confused by your area pie chart, John, because you included the tag controller in it, and you were only talking about the core.
Yes, I didn't talk about everything we'd done, but this is the area overhead of the entire FPGA design that we have. So, yes, I didn't talk about the tag controller.
Okay,
that'll be another talk. Hopefully we'll have, partly that's because we haven't finished improving the tag controller. We have a lot of ideas how to make it better. Honestly though, Codasip has a tag controller that's far more sophisticated, and so we're not going to approximate that, sadly, but we will improve on what we've done previously.
Okay, thanks.
Hi, John. Thanks. Great talk. I was going to ask, you said that now the issue stage is the one that is in charge of the PCC bounds, right?
Yes.
How do you do, because you need the bounds of your PCC when you're doing instruction fetch, right? So how does the instruction fetch part of your execute stage know about the bounds?
So I don't know if you're going to like this answer, but anyway, we just chill out and don't worry about instruction fetching instructions that are not inside the bounds of PC, because we have a chance to throw an exception, and you won't architecturally see that those instructions were fetched. And if your blood pressure is rising because of transient execution vulnerabilities, we would believe that unless you have some timing sensitive operation on the instruction bits, it's difficult to leak the contents of memory through. So I can't promise what we actually do, but as long as you catch your bounds violation before you execute, it's unlikely that your decode is timing sensitive to the bits that it got. Hopefully that's helpful, and there's lots of good arguments to have about that. But anyway, that's what we've done so far.
That was, we don't have any more time for questions. Let's thank the speaker again.
Thank you.